So let's start looking at possible implementations that we can get for the FIR filter by using the concepts of projection and scheduling according to the systolic array architecture. To recap, what we have is the FIR filter that we are looking at is something of this that follows this equation. W0x of n plus W1x of n minus 1 plus W2x of n minus 2. And the dependence graph that we obtained for this essentially has the x values as vertical lines but increasing along the x index increasing along the horizontal axis, and the three values W0, W1 and W2 for the weights increasing along the vertical axis. The cross nodes essentially correspond to the computations, and as we saw, the dependence graph that we constructed had the y values being propagated along the bottom right direction. And so on. Let's take this and start by choosing different values of the projection vector and try and see what it corresponds to in terms of hardware. Alright, so the choice that I'm going to start with is what is considered in the textbook as design F. This essentially corresponds to a choice which says D is equal to 1, 0. And we need to choose, once we have chosen D, automatically it means that we have to choose a value of P which is orthogonal to this value of D. One simple choice is to go with 0, 1. Notice that this is not unique. Even if I had chosen 0, 2, for example, it would have been orthogonal to the D vector. Right? So in other words, the choice of P once you have fixed D is not unique. There are multiple different ways by which you can choose a given value of P. Not all of them have physical meaning, and what we'll find is that in a lot of cases we might also have to make certain kinds of adjustments to our dependence graph for the interpretation to be meaningful. But in this case we will just stick with the simplest possible interpretation and see where it takes us. I also need to choose a value of S. The only constraint on S is that S transpose D must not be equal to 0. One example that I can choose over there is 1, 0. As you can see, 1 minus 1 would also be perfectly valid, 1, 1 would be perfectly valid, etc. All of those would give me S transpose D not equal to 0. But with this set of choices, what can I do about the computation of the three edges that I have in my system? In other words, if I have ij as the location of the ijth node, what I actually have is a w which is along the axis 1, 0 or along the direction 1, 0, x which is along the direction 0, 1, and y which is along the direction 1, minus 1. So what this tells us is that the node ij is mapped to processor number P transpose into ij, which will basically be equal to 0, 1 into ij is equal to j itself. And what is the time when it is mapped? That is given by S transpose ij, which is 1, 0 into ij, which is equal to I in this case. Notice that I is the horizontal axis, j is the vertical axis. And let's see what that translates to in terms of what the hardware architecture looks like. Before we can construct the hardware architecture, there is one more thing we need to know, which is what do each of these edges, the W, X, and Y edges, map to? We can just create a small table for that, which basically says this is the edge number. For the weights, the edge was 1, 0. The P transpose E that it corresponds to essentially is P transpose 0, 1 into 1, 0 gives us the value 0. And the S transpose E is, in this case, S transpose being 1, 0 and W also being 1, 0, the product becomes 1, the dot product between the two. What about the inputs? X. This corresponded to a vector 0, 1. Right? We can see that from up here. In other words, this W corresponds to this, the X corresponds to this, and the Y will then correspond to the next value that we have over there. So with X corresponding to 0, 1, what we find is that P transpose E corresponds to 1 and S transpose E also is equal to 1 in this case. I need to make a correction over here. The S transpose for the case that we have over here actually corresponds to a slightly different value. It corresponds to the value 1, 1 and not 1, 0. Okay. What that means is further that with this value over here 1, 1 and ij, it corresponds to I plus j for the time at which the ijth node is going to be scheduled. All right. And finally, what we have is the outputs which correspond to y, which corresponded to the vector 1, minus 1. When I do P transpose E, that corresponds to a minus 1 for the value of P transpose E and 0 for the value of S transpose E. Now, all this is fine. Mathematically, everything is consistent. We know that in principle, we have done something which seems to be mapping a certain set of computations onto a hardware architecture, but it's still not intuitively clear what exactly this means. So let's translate these numbers into an actual hardware architecture. The way to do that would be to try and draw something like a block diagram that indicates what are the computations as well as the movement of the data that we have over here. What I'm going to do is to say, I will look at 3 different processor values. Why am I taking 3 processor values? Because as you can see over here, the J corresponding to the weights is in the value 0, 1 or 2. In other words, there are only 3 possible values that the processor number can take. That basically tells us that I can think of this as processor number 0, processor number 1 and processor number 2. What happens to the weights? If I look at this value, it says that on every clock cycle, that is to say, with a delay of S transpose E is equal to 1, where should a given weight move? And this answer 0 essentially says that the weight remains where it is. So in other words, if this had the value W0, on the next clock cycle, it would still have the value W0. And of course, the way to indicate this is to say that there is a 1 cycle delay on it, right? Now you might wonder why we are even drawing something of this sort. After all, doesn't it just mean that the weight remains where it is? Yes, it does. This is just a way of making that edge, the weight transfer edge, explicit in this case. This will become a bit more clear when we look at other architectures where the weights actually move from one clock cycle to another. This in turn means that W1 also looks like this and W2 remains on P2. Alright, now what does this edge over here corresponding to X imply? what it says is that on every clock cycle, the P transpose E is equal to +1. In other words, when I go from one clock cycle to the next, I need to transfer the data to the processor on the right. In other words, I need to go from processor P0 to P1 and from processor P1 to P2, and each of these with a sample delay of 1D, right? So in other words, this corresponds to this edge and this one corresponds to the D that I have over here. Okay. Now, to keep the structure completely regular, I will also draw an arrow which comes in over here, but that's just corresponding to the input, so I do not really need to indicate it as having a specific value. There is also an output edge over here, but where does this go? Effectively, what we are saying is that I just discard it. This does not really correspond to a value. This is just propagation of the input. What is more important, on the other hand, is what happens to the Y value. And if I look at this, what I can see is, number one, the value needs to propagate towards the left. In other words, from P2 to P1, P1 to P0, etc., because the P transpose E is -1. But it also says that S transpose E is equal to 0, which means that I need to do this propagation without having any delay on that edge. If I draw it, it would look something like this. And I would have these leftward edges that are going from P2 to P1, P1 to P0, and from P0 to output. Okay. Does this correspond to a physical architecture that we are probably already familiar with? Yes. Effectively, what this is telling you is that this corresponds to X of n being multiplied by W0 over here, being passed through a single delay element, being multiplied by W1, another delay element, and being multiplied by W2, and now finding its way back by means of additions that happen in each of the computations. So the X of n over here is the input, Y of n is the output, and these are the weights. And what we can see over here clearly is that one such block corresponds to a processing element. What does this architecture look like? This essentially corresponds to what we would normally call the direct form 1 FIR filter architecture. Okay, so how did this happen? If we go back and quickly recall what we did over here, we can see that we started off with a choice of values for D. This was in some ways derived from D, and this was also chosen, right? So D was chosen, S was chosen, and the P in some sense was derived from D. Of course, we need to make sure that P transpose D and S transpose D both satisfy the properties that we require of them. We then looked at these two properties, which says that a given node is going to be mapped onto which processor and at what time. But more importantly, we need to look at these three edges in our dependence graph and see where they get mapped onto. We found that we can create this table. By translating this table into a hardware architecture, it ends up looking like this block diagram. And this is our actual architecture, the one that we are most familiar with, the direct form 1 FIR filter. To show that this was not just a simple special case, let's consider a couple of more examples. In particular, we will go and take a look at what is considered as design B1 in the text. Over here, what we are going to choose is D is equal to 1, 0. P once again is the same, 0, 1. And S in this case, we will choose the value 1, 0. Right? Unlike the 1, 1 that I had earlier. Let's see what architecture this gives me. Once again, I have the same thing. Node ij will map to processor j, right? That is to say P transpose into ij at time I, which is S transpose into ij. Okay. What do the edges map to? We can just write down the P transpose E and S transpose E values over here. The weights correspond to the edge 1, 0, which has a P transpose E of 0 and an S transpose E of 1. The input X corresponds to 0, 1, which has P transpose E equal to 1, S transpose E equal to 0. And the output Y corresponds to 1, minus 1, which corresponds to a P transpose E of minus 1 and a S transpose E of plus 1. What does an architecture for this look like? Or a block diagram for this? Once again, the weights remain where they are. The processor ID, given that it is equal to just J, this is once again in the range 0, 1, 2. Therefore, I have 3 processors. With W0, W1 and W2 remaining where they are. As you can see, this essentially conveys that it remains in the same place. This propagates to the right and the results propagate to the left. What does that mean? Once again, let me fill in the rest of the arrows. The input propagates right, but you will notice that this is without any delays on it now. S transpose E is equal to 0 for the input. The result or output, on the other hand, propagates to the left, but with 1 D. What does this mean? Once again, does this remind us of any architecture that we are already familiar with? Let's try and do that also. What we can say is, because of the zeros on these edges that we have over here, I can essentially draw them as one single straight line. The computations correspond to multiplication with W0, W1 and W2, and I then have the additions that happen as the data flows backwards. Hopefully, you can recognize this as the so-called direct form 2 implementation of the FIR filter, right? And what we can see, in other words, is that by a simple change, which was just a different choice for the value of S while keeping the D and the P exactly the same as before, I ended up with a different architecture that was obtained by using just the same precise mathematics as in the previous case, and obtained the direct form 2 FIR filter. Now, what are the differences between these two architectures? In the previous architecture, we would normally say that the weights are remaining stationary, meaning that the weights remain on the same processor from one clock cycle to the next. The inputs propagate or move, and the output also moves, but in a special way, meaning that it is basically broadcast. What's the difference between move and broadcast? Move indicates that from one clock cycle to the next, it moves from one processor to the next. Whereas broadcast means that it moves from one processor to the next, all within the same clock cycle, right? In terms of VLSI architecture, these have very precise implications. Broadcast, for example, means that you need to have one long wire that goes all the way from one end to the other across all the processing elements. Whereas a move with a delay on it means that there is a short wire that connects one processor to the next. What does this mean for the direct form 2 architecture? Over here, what we have is the weights once again are stationary. The inputs are broadcast to the right, and the results or outputs move to the left, one clock cycle at a time. You can once again see why something like this would be called a systolic array architecture. On every clock cycle, you can see how the outputs sort of move from one processing element to the next until after 3 clock cycles, they have come out on the left hand side. But during that time, there is also another partially computed output that is sitting at the output of P1, and similarly another partially computed output at the output of P2, which are making their way slowly towards the left, one per clock cycle. To complete this, let's just take one more example. Here we have a completely different choice of D and therefore P. We need to make P transpose D equal to 0, so we will choose P as 1, 1, and the S transpose, in this case we will choose as 1, 0. In some ways, what this is telling you is that now that you have reduced it completely to a mathematical set of formulas for mapping, you could pretty much choose any value of D and P and S that satisfy our requirements and come up with different architectures. The problem is not all of the architectures are meaningful or useful. So how you choose the D and P and S values is still to some extent a question of experience with the kind of designs that you are trying to do. So like I said, what I'm going to do over here is just consider this example in order to show you what are the values that what kind of different architectures can be created by using these techniques. The most important thing for us is once again going to be the mapping from the edges to time instance, weights 1, 0 gets mapped to 1, 1. In other words, in terms of our interpretation, the weights move to the right. Now, what does that mean? It basically means that a weight is going to get moved from P0 to P1, and then from P1 to P2, and then from P2 to where should it go? We don't really have a requirement for more than 3 processors, but this is where, as I said, some amount of interpretation of the results also matters, because the equations just tell you that after moving to P2, the weight will then move on to P3. But we know that we do not require more than 3 processing elements because there are only 3 distinct weights to be computed. And if we look more carefully at the dependence graph, we can find that P3 can then be mapped back onto P0 itself. We will make use of that when we finally construct the architecture. What about the inputs, which is the edge 0, 1? This corresponds to a P transpose E of 1 and S transpose E of 0, which basically means it is being broadcast because S transpose E is equal to 0, and to the right because P transpose E is equal to plus 1. What about the output Y, which had a vector of 1 minus 1? This corresponds to a P transpose E equal to 0 and S transpose E is equal to 1. Effectively, what it says in other words is output is stationary, remains in the same place, remains on the same computational element. Now, what does this mean in terms of hardware architecture? It's a bit more tricky to interpret this. Effectively, what it means is that we have results that are now remaining on the same processor, weights that are moving from processor to processor, and inputs that is broadcast across processors. Right? Redrawing this, I can think of it in terms of the multiplication and an accumulation and holding the value that all needs to be done in the same place. The switch that I have over here essentially allows me to switch between either a 0 in order to reset the value every 3 clock cycles, or the previous accumulated value to come back into the design, right? And what we have over here is the other input to the multiplier essentially corresponds to the weight value, which will take the sequence W0, W1, W2, W0, etc. So you can see that this is kind of an interesting architecture. Effectively, what is happening over here is that the weights are now going to keep changing. And the inputs are also going to keep coming in, but broadcast. Why would anyone want to create an architecture of this sort? That's not entirely clear whether you would actually benefit from something of this kind of a structure. But at the end of the day, what it's telling you is that this also can be used in order to create the same final output, right? And by having this computation, you can essentially compute each of the results by propagating the X as well as the W values and finally getting the results at a single processing element itself. Also note in this case, one more thing, you might wonder why you need 3 different processors if after all everything is being done on the same processor. That's not entirely true. Effectively what this is saying is Y0 will be computed on this first processor, Y1 on the second one, Y2 on the third. Then again we get back to Y3, Y4, Y5 and so on. Okay. So in other words, the 3 processors are each computing a different processing output by appropriately broadcasting the inputs as well as moving the weights from one place to another. For completeness sake, there's one last example that we will consider over here, which is considered as design R1. The reason this example is interesting is because it is a case where the hardware utilization efficiency is less than 100%. All the others that you can see so far have a hardware utilization efficiency of 1 or 100%. In this case, what we will choose is D is equal to 1 minus 1, P is equal to 1, 1, and S is also equal to 1 minus 1, same as the D vector. What you can see is that therefore S transpose D is equal to 1 minus 1 into 1 minus 1, which has the value 2, which implies that the hardware utilization efficiency is equal to 1 over 2, or in other words 50%. What does this mean? If you go through and do the mapping of all the edges, you will find that the resulting architecture looks something like this, and I'm only going to draw the final architecture itself without going through the computations. The weights will propagate right with a delay of 1 sample. And what we will find is that the inputs propagate left. Or to be more accurate, I should provide the inputs from this side. Right? So the inputs basically propagate right to left, but once again with a delay of 1 clock cycle. What this in turn means is that results now remain on the same processor with a 2 sample delay, meaning that they remain there for 2 clock cycles before they get back onto they essentially pass through 2 registers before coming back to the same point. Why is this kind of an architecture useful or interesting? Effectively, the important point over here is that if I design this unit over here as a VLSI block, I find that all connectivity between blocks, all the edges have registers on them or delay elements. Why is that a good thing? Because when you are constructing a large array of this sort, it means that the routing that you need to worry about between processing elements is restricted to just short wires. You do not ever have to broadcast a value, which means that you do not need long wires that go across multiple processing elements. Is this worth it, and is it worth the loss of hardware utilization efficiency, which basically drops to 50% as opposed to 100% in the previous cases? In this case, it is not at all obvious, because after all, this is a very simple filter structure that you are creating. But there could be other kinds of options where you might find that having this structure that allows you to trade off the hardware utilization efficiency for having shorter wires might actually be a good thing. With this, I'm going to conclude the discussion of systolic array architectures. As you can see, it is just a very high level overview of the process by which we can take a dependence graph and map it onto a given architecture. The main things that I want you to focus on as far as this particular coverage of the topic is concerned is that we are assuming that there is some way by which you can already create a dependence graph, and the only thing that we are really looking at is what are the properties to be satisfied by the projection and scheduling vectors, and how do we go about systematically taking a set of values for projection and scheduling vectors and converting them into a hardware architecture. More importantly, we also looked at the specific example of the FIR filter in order to see how that gets converted, how we can take a single dependence graph and convert it into different architectures for an FIR filter, each of which has a different set of properties. Systolic arrays themselves are used in much wider contexts. They are typically used for much more complex kinds of operations. Matrix multiplication, matrix transformations, inversion, factorization are some examples where systolic arrays perform very well, and various kinds of image and other signal processing applications also. The details of how to take a given signal processing algorithm and systematically convert it into a dependence graph that can then be mapped onto various kinds of hardware are beyond the scope of what we are covering in this course. And on the other hand, if you are interested in those, then hopefully this should give you enough of a background that you can understand the basic concepts involved and then go into those topics in more detail.